Welcome again. Welcome, everyone. Next panel. Important question. Should we commit to an early orbital mission to Mars? Tim Cichan is the moderator of this panel. Lockheed Martin Company, of course, one of the big four amigos. A big thing to be. Space exploration architect, that's very important for us because we're still kind of figuring out how exactly we're going to do all these things we want to do. And getting robots, astronauts to visit the moon, the asteroids and Mars. Personally, I'm never so interested in the asteroids. As someone once wrote to me on my Facebook page,
unless it's coming our way.
Yeah, okay, but then it's not about walking around on it, is it? Then it's, I don't know what you do then, shooting it out of the sky. It's probably too big for that. And you just get more pieces, you know. And if I get the Meteor Hollywood movies right, it's even more trouble. So that's not a good idea. Well, without further ado, I would say, Tim, get your panel in order and tell us how to do this.
All right. Thank you. So I want to have a discussion today with these great panelists to sort of explore the various both benefits and risks of an early orbital mission with crew. And so this session is all about getting ready for humans to Mars. And humans to Mars can be interpreted in different ways. Is that humans in the Mars system? Is that humans in orbit? Is that humans on the surface of the moon? And of course, the horizon goal is always humans on the surface of the moon, of Mars exploring. But what do we need to do to get ready for that amazing mission? We heard about precursor missions, but what about going into orbit? Do the benefits outweigh the risks? And I think that'll be the theme of this panel. And there's a lot of different various flavors of benefits and risks, and I hope that we can explore that and all the different varieties there. So I'm Tim Cichan. I'm the Lockheed Martin Space Exploration Architect. I lead a team that explores mission concepts for humans exploring Mars, their robotic partners, as well as precursor missions at the moon. And I'll introduce the panelists real quick, but they'll take their own time to kind of introduce their background and their points of view. So Joe Cassady here is the Executive Director for Space for Aerojet Rocketdyne, as well as on the Board of Directors for ExploreMars. Jen is from NASA Goddard, Planetary Geochemist, and will provide that great science perspective that is an important part of human exploration. And Rick at the end, NASA Science Mission Directorate. He's responsible for the landing site selection team, Mars reconnaissance efforts there at SMD, but he also has a great wealth of experience in ISS operations. But to kick things off, it really is a complex set of those benefits and risks when we talk about crewed missions to orbit Mars. And of course, there's the technical aspects of that, both from an architecture point of view, from the different vehicles and elements that are traveling to Mars, the subsystems and systems that support the crew, but also just as important, or perhaps even more important, is the operations of doing missions to Mars and the logistics to support those operations. And perhaps, the first missions to Mars don't have as long a logistics supply chain, but the intent there is to continue exploration, and getting ready for logistics, I think, is one of the topics that we'll explore here. So that's the technical part of it. There's also the scientific piece and sort of the overall question of, with crew in orbit, how does that enable science, and how does that science kind of fit into the overall scientific and exploration campaign at Mars, and what value does it bring? There's also a flavor here of the schedule and the technology development roadmaps, and can an orbit mission fit into that schedule? And I think that the key theme that we'll hear, right, is that the landers for going to Mars is one of the longer leads on the roadmap. And so if, like on the Apollo program, if the lander's not ready, there's still a lot of great work to be done, or is the risk too high and we should wait for the lander? And I think we can't, it's human spaceflight, so we can't forget about both the policy, political, and budgetary aspects of this. And how does an orbit mission fit in? Does it help with budget profiles? Does it give policy wins? Or is it a distraction or something that slows us down? And I think that that's kind of the debate there. And the way I'm thinking about, kind of from a timing perspective on the panel, about 30 minutes for the panelists to introduce themselves and their areas of expertise. About 30 minutes of questions from me, get a good discussion going, and then about 30 minutes for audience questions. So with that, I'll hand it over to you, Joe.
Oh, okay. Do I have some charts?
You do.
Oh, great. I'll wait for him to come up here.
Name.
Oh, Cassady.
Joe Cassady.
There we go. Yeah, I particularly wanted you all to see this chart. Yeah, remember that one, Hoppy? So this is something that Hoppy and I were responsible for, and you heard him talking about it a little bit this morning. The charter, this was at one of our AM workshops 2 years ago now, I guess, almost. And we had been broken out to be the guys who figured out what could we do on what we called the sortie campaign, but our way of looking at it was, this is the cheap way, right? So we even have it in Latin up there, to Mars on the budget, And that's really what we were all about. And I think I found that El Cheapo from some thing on the internet. That's a gas station down in Georgia or something. But that was our kind of mantra. And so Hoppy, I think, actually showed this one this morning too. What we did is we said, okay, if we had to do something really fast, and the goal was here, let's get something ready that could fly in this 2033 opportunity. And so, we went away from all of those things that were high-risk development type paths, and we tried to say, what's existing now? And we had a really good crew of folks on our team. I almost put the team chart in here too, but we had a good breadth of experience from different places. And we said, okay, we can build on this stuff. We're assuming Orion's there. We've got an Earth departure stage that we built out of existing engines. This was all storables. There's no cryos here. I don't think the EDS was even cryo. It could have been because we just used it. Yeah, I think we left that open to trade. Yeah, and it was a commercially available thing. But we built this thing up to be, in some ways we were inspired, I think, by the Mars base camp architecture that Lockheed Martin had shown a year or so before. And we said, we want something that sort of follows that path, but without a lot of the other bells and whistles. So, even the power systems here and the trans-hab and things like that were all sized to be something that was kind of like not a big development risk. And so this is what it looked like. We had the Orion, we had the trans-hab itself, we had a TEI stage that went along, a Mars orbit insertion stage, and then the Earth departure stage. So, you can see it's a classically staged vehicle. Gave us a total mass of the stack of about 150 tons. And we were set up to, let me go to the next chart. This kind of gives you the mission sequence. And this is why I'm talking about it here. We said one of the tall poles that we didn't think we could get ready by 2033 was the EDL. So by going and doing this in 2033 and going to orbit only, we could still achieve those goals, as Tim said. We could take advantage of that 2033, really good opportunity to go out to Mars. We wouldn't have to do a really compressed development on some of those other technologies that would make us bust the budget. And then we thought about it and we said, and we could use a sky crane mission and we could still deliver some kind of unpressurized rover with a lot of cool science equipment that we could teleoperate from orbit. And so that was kind of the construct that we came up with. And then that would set us up for going again in 2037 because we've now checked all this equipment out. And so we'd be ready to go. We'd have that full mission checkout. And then we could also include the lander for a 2-week landing sortie in that 2037 mission and again in 2041. So that was kind of the way that we avoided the bump in the budget by just sort of letting it spread out. And then, obviously, as we got into those that cadence of missions, then we would start to on-ramp some of the more advanced technologies. We could bring along the landers and the pressurized rovers and things like that as the development allowed it to happen. And that also then would give us the ability to try to have a flight rate that was basically every other year. Every Mars opportunity, we'd be able to send a new crew out and go to another site. And that was another advantage of our approach. Since we were doing sorties, we said we don't have to pick a site. We can decide every time if we want to go back to the same place or if we want to go someplace different. So this is what it looked like. It boiled down to something like 3 SLS launches and a commercial launch of that Earth departure stage. And you can see, essentially how we sort of aggregated things, put them together, put the whole stack up into a high Earth orbit where it was a good departure point, and then finally we launched the crew up in Orion to meet up with that stack, and then we left for Mars. Took us a total round trip time of about 950 days. Of which we spent about 450 days in a high Mars orbit doing the actual mission at Mars. So, a good fraction of the total mission is in the Mars vicinity, operating that rover, doing other things that, inform us. And obviously, every element of the system gets checked out, and then, we come back, we break Orion loose and re-enter the crew in the Orion capsule. So that then sets you up to do this in the follow-on missions. And as you can see, and this was a lot like what Hoppy showed this morning.
Pretty much exactly what
I was going to say, I think that is the chart you showed this morning. But basically, again, everything except for I think the SEPTUG, it was already demonstrated in that previous mission, and I think that one just didn't make it on the cut on that previous one. We actually had talked about it maybe being something. The reason it's on here is it's delivering the Mars Ascent vehicle out to Mars in advance of the crew going, because obviously if you go to the surface, you got to get back off the surface, as we all know from The Martian. It's good to have a Mars Ascent vehicle handy. And so we just pre-deployed that with the SEPTUG in this one. And I think this just shows kind of the overview of all the elements that would be required to do that, and the various launches. And again, I think the other thing that we found in this, as we looked at this, budgetary version of this, really squeezing down and not doing any technology development, is it does allow for a good blend between what we would do with SLS, what we would do with things like Orion as still the backbone, but how we could bring in commercial and use those in conjunction with the SLS launches to be able to accomplish this. And you can see also from this one which launches have limited launch periods and which ones are more flexible in order to achieve it. And that's kind of how that whole crew vehicle stacks up then for the lander. And it's a slightly modified EUS, which is another element that's already part of the mainline plan. And that was basically it. So we, I think the key thing there was going through that with a team that was pretty well informed, knew the technologies and things like that. We felt like we could pull something like that off, and you didn't have to have any kind of increase in the budget. That was really what we set out to do, and coming out of the workshop. And I think, Hoppy, you've looked at it a little bit even beyond that. Nothing's changed our mind since then. Yeah, and all those things that the Stippy report, basically was saying we're going to be tough to do by 2033.
We weren't doing any of this.
We weren't doing any of those. So that kind of takes care of that. And you also don't have, with the orbital mission, you don't have to work the EDL problem, which is in our other workshop. I can't remember if it was the one before or the one after that, when we looked at the tall poles. That was the one that we found was the hardest one to squeeze down to less than about 15 or 16 years, just because of where we are now and where we need to get. So that's what I had.
All right. Thanks, Joe. Jen.
Okay, so I'm going to tell you a little bit about the science that could be enabled by a human orbital mission. A little background first. I'm at NASA Goddard. I'm a planetary geochemist, and my group works to develop instrumentation to measure the composition of the surface and atmosphere of Mars and planets and planetary bodies beyond Mars. I'm involved through that group with the Curiosity mission. We have an instrument called the Sample Analysis at Mars instrument, and so that is my perspective. I'm coming from the perspective of somebody who likes to actually be on the surface and get my robotic hands into things. But after really sitting and thinking about it, what I really think there's quite a bit of science that could be enabled by an orbital mission as well. Okay, so one of the main attractions are that you have by going to orbit and orbiting for 450, for a long period of time, you have access to this unique environment, and you can do these long-term studies on the human body and on more than the human body. You can do growth studies. You can expose, basically you have all of this exposure to microgravity and radiation, and it's really different than what we have in Earth orbit. As you can see here, ionizing radiation is basically blocked by the Earth's magnetic field, and so even on the ISS, you don't have the same kind of exposure, as we know, to radiation as you would orbiting Mars and in particular on the way to Mars. So that's really unique, and certainly, there's a history of doing studies on the human body. One of the most popular and most well-known one is the twin study. So there's quite a bit that could be done just to understand how our bodies are able to endure these conditions. Other experiments that can take advantage of access to deep space, growing micro and macroorganisms. Something else is space telescopes. So a lot of spectroscopy that's Earth-based is hampered by the fact that you are looking through Earth's atmosphere to see, basically into the distance, to see distant objects. And that's why we have something like the Hubble Space Telescope. So you could deploy, telescopes or spectroscopic instrumentation from cruise or from orbit, and you're not looking through atmosphere. So that's something that's definitely a benefit, and that we simply can't get by being on the surface of Earth. There's also actually something I was thinking about is heliophysicists have studied the sun mostly from Earth, but they haven't studied it from further out, from Mars, and that's certainly relevant in terms of looking at what would an exoplanet see in terms of that kind of distance from the sun. In addition, I was reading about an experiment on the ISS where they take aerogel and they basically stick it out and expose it to space debris, and it's actually an astrobiology experiment, and you can capture IDPs, interplanetary dust particles. So imagine if you are able to stick something out on the side of a spacecraft on the way to Mars and expose it. You can really build up a large concentration of these things, which are really hard to measure. And not only that, but you have people on board, and if you have a laboratory, you have people who can do some basic analysis of these things. So that's another benefit of having sort of this captive audience, this captive workforce on a spacecraft, is that you, with even some basic laboratory instrumentation, you can do quite a bit of science, as well as bring some of those particles, some of that material home to do further science. So that's a really big benefit that you have. You actually have not only you're able to capture these things, but you have people on board who are able to do the work. Something else that if we're orbiting Mars, if you take a look at these are from MRO instruments, CRISM and HiRISE, and what you see here is these sort of strips. And this is how we basically image the surface of Mars now. We see strips at sort of a time snap of Mars, and then you sort of mosaic them all together. And if you're actually on Mars orbiting, you are able to do some discovery-driven science. For example, the MAVEN instrument, which is a Mars orbiter, was orbiting Mars when a comet, Siding Spring, just happened to come very close to the upper atmosphere of Mars. And they were able to make measurements that they wouldn't that they were just, happened to be there. It was very opportunistic science. So having humans in control of what that orbiter can do enables them to really react to what they see as the data comes in, and then do more science. And some other sort of more ephemeral processes that can occur on Mars is ice sublimation, transient water. Impacts can change the surface and impact the atmosphere as well. And then things like dust devils. So there are a lot of things that if you have somebody sitting there sort of watching what the surface looks like, you can basically do a lot more opportunistic science. Another thing you could do is a detailed assessment of landing site, because you're simply out there for a long time and you have the ability to make decisions much more quickly than you would if you were doing truly remote science, where you're basically everything is going back to Earth and being relayed through a large science team that can never make decisions on their own without taking a long time. So there's some benefits there. And then, of course, if you have assets on the surface, and we certainly do now, and we certainly would have more by the time we're talking about this kind of mission, you can do telerobotics. You can control those assets on the surface. And both ESA and NASA are invested in development of telerobotics. So there's a lot of creativity. Even though you don't have humans boots on the ground, you have the next best thing. You may have robotic assets that can do things almost, as we say, joysticking. So you can't joystick, for example, you can't joystick the rover, the Mars rover, because of the comm delay and because of a number of just how hard it is to get information back and forth. If you're orbiting Mars, you can do that sort of thing. And then finally, Mars 2020 mission has a plan to cache samples. It's going to take little cores, and it's going to put these cores in a canister up here. And these samples eventually the intention is to return these to Earth for study. But there's no specific identified mission that's going to do this. So, and the architecture to actually return these to Earth is not so different than what you would do for humans. You have to launch some sort of MAV, and then an orbiter has to rendezvous, take these things back to Earth. So you could imagine perhaps these samples could be brought back to an orbiting asset with scientists ready to do some analysis for an orbiting mission by a MAV. And so this is just sort of an example of that. This basically you have the MAV launching and being grabbed from orbit. In this scenario, these are taken back home to Earth, but you could certainly do some triage, and of course that may prevent. Some people are worried about contamination of backward contamination of Earth. So if you actually are doing work on these things in orbit, you can at least triage some of these samples for possible contamination. And I think that's it.
Thanks, Rick.
If we can go to this deck for Rick Davis. I'll get there. Is there something I'm supposed to do? Okay, I'll just wait. So I'm Rick Davis. I'm with the Science Mission Directorate, and I do a couple things. I co-lead the process to pick a human landing site on Mars. I'm the lead for what we call reconnaissance in the Mars exploration program, which is distinguished from science because we are increasingly realizing that we need to look at those both separately so that we make sure we have a fully balanced set of priorities. And so, and then in general, they kind of overlap like 90%, but there are differences. So, for example, weather has been sort of underrated in the past, and we're trying to raise the priority on that because we know we need it for human spaceflight to Mars. So you'll see those kinds of elements there. And so we got the slide deck. Great. Okay. So I'm calling it Stepping to Successful Sustained Exploration of Mars. And what I'm trying to would like to do is give a sense of what we've learned in the Mars exploration program in terms of stepping things. But then I do have some human spaceflight experience because I was in mission control for 15 years. I worked in Russia for 3.5 years, and I've seen a lot of international programs. And so when I see what MEP does, then I map these other things. There are some really kind of fundamental principles that I think that we can build on probably. I love this picture; it's just totally cool. But I want to launch off on this a little bit because this one is really the key part. There are risks that we know about, and there are risks we don't know about on a mission to Mars. We're really good at mitigating the risks that we know about. We are crappy at mitigating the risks we don't know about because we try to get those others so safe that what we don't realize is that the real risk to a crew is the aggregate of the two. I'm going to show you some slides from the original expedition to ISS in a little bit where it was just a tiny space station. We're so used to seeing a big honking space station, we assumed it always exists there. But when Bill Shepard, Sergei Krikalev, and Yuri Gudzenko went up the first time, they knew they were pioneers, and they knew they were going to run smack dab into all those risks that no one had thought about. And that was a very painful period, but ISS has been incredibly insightful in terms of how to manage that. I would even argue that ISS is really the paradigm we need to be thinking about when it comes to a Mars transfer vehicle and what we expect of it. But that's a key piece. The next piece, which I would allude to, is many of us deal with budget for spaceflight. And the challenging piece about Mars, if you're not careful about it, it ends up being unobtainium. And essentially you end up having 10 programs running simultaneously if you look at the end state. And for me personally, I increasingly view it as it's impossible. It's really a question of sequencing. How do you phase in things in a way that doesn't break the bank and yet produces real value? And we really need to, we've done that in the Mars exploration program. I would actually argue we've done that in every successful program, going from ISS to shuttle to, even the Europeans and the Russians have gone through the same process. It's the phasing. And the cool part is that we did the original architectures where we took swags at mass and, that kind of thing. Now we're in the phase where we're actually worrying about phasing. And we're going to find that some of the things we swagged weren't right, but we'll get there. And one of the things I think we weren't right on is that I did a shuttle mirror where we were told, Merry Christmas, this is foreign relations, we're putting people on board the Mir space station, go make it work. The problem is we had crew members that were sitting on board that space station without enough to do. And I was in Russia at the time, and so what we did, we went debriefs with the Russian flight control team. And in Russian traffic, it is not uncommon that a 28-minute ride morphs into a 3.5-hour ride, and you get very close to the people that are in that van with you. And I was actually surprised at the consistent frustration levels of crew members, and this is just a 6-month mission, that did not have enough work to do, meaningful work to do. And we have really got to think about that for Martian missions. I personally, after having lived through the shuttle Mir experience and the early ISS days, will tell you that that strongly suggests there's a pretty robust lab going on in the MTV, and that we are really trying to look at serious science that we are trying to do. And on the ISS right now, Katie Bogstader probably knows the number better than I do, but with 4-person crews, I think we're targeting 35 what we call utilization hours per week. Yeah, but that's with a larger crew, I think, right?
That's really what we're targeting.
Yeah.
Although we probably say that's extra, bonus.
But we fight for that time, is the point I'm trying to make. And then to imagine a missions, I'll say it plural, into regions of space that human beings have never been into, and to say that we cannot figure out ways to keep them productively employed doing the amazing kinds of science that Jen just described, or just even, and a whole range of other things that we probably don't even know about because we haven't really started that conversation as much as possible, is insanity. And we can say we don't want to carry the mass, but the reality is that we're going to have to keep those crew members busy, and they're not just sitting there in stasis. We've got to figure out a way to really use them and maximize the return on investment that we would be making. And I personally believe, having watched ISS, there are lots of amazing ways to do it. There is a mass penalty involved, but we're going to have to pay it anyway, I believe. And I think the lessons of ISS scream that. And then another thing that comes up, and I'll talk through these analogs in a moment, is well, there's a radiation issue. Well, from my perspective, I worked STS-77. We spent 2.5 years getting a satellite ready, and then all of a sudden when we went to do it, the attitude control system crapped out, and 2.5 years of a lot of people's lives were flushed right down the drain because we couldn't even release the stupid satellite. That was STS-60, actually. And so the point I'm trying to make is you get it all the way out to Mars. You spend 7 to 8 months to get out there. You have to handle the contingency of a lander not working, in which case you're in an 1,100-day orbital mission whether you want to or not. And so that science profile and plan already has to accommodate this. And so I think we really need to be thinking about that. And Jen did a wonderful job outlining some of the things. I actually think there's going to be another area that is sort of very fertile for thinking right now, which is using potentially landed assets with the crew operating to prepare launch pads, or doing other civil engineering type tasks, which we probably want to do. I can tell you, because we just supported an entry, descent, and landing as plume impingement, Tim, that we had internal to the agency, but there's going to be more publicly eventually. And plume impingement is a big, big problem. And we do not land big honking rockets on this planet. Well, we hardly do land rockets, right? We're usually taking off. But the point being is we have tons of concrete under those things. We have, sound attenuation. All those things we worry about. And I think that as we get into this next phase of more detailed temporal phasing, we're going to end up having to deal with that as well. And so that is another source of tasks that we probably were going to really need a crew to be thinking about doing. And the last component, and it's a couple of historical analogs that underscore some of these points, is the budget profile. And, we cannot ignore budget. So if you have 10 things, I'm talking like if you're trying to pay for heavy lift capabilities, which are largely done, if you try to pay for that, for Mars transfer vehicle, for Mars landers, Mars ascent vehicles, Mars surface suits, you're paying for HAB labs, and then all these things, they cost a lot of money. And we really have to think about that phasing so that we can make it affordable and doable, driving back to the point that if we've got to go sooner than later so that we really understand those other risks, and like Expedition 1 did, so that we can start mitigating them. Now, if I can do this, I'll just hit on a few. I'm not going to go to this point other than the fact that a lot of times people view, a few of you were in the last talk that I did, but the Gale crater, I love this picture, it's totally rocks, right? And then a lot of people go to say, it's just like Jordan. And no, if it's just like going up K2 times 1,000, if not 10,000, and I just went up a coat epoxy in Ecuador last week, and I will tell you that is not a simple thing, and we need to be very respectful of that reality because that's what we're dealing with. So a lot of times people push to the surface, and I will tell you, if you're in a Houston flight control room, if you had a paradigm or mantra, it would be in space is dangerous, on the surface is safe. And I am shocked at the number of people who take that and apply it to Mars and say, in space is dangerous, on the surface is safe. We have 60,000 human days in space. That's across all platforms, Mir included, and Soyuz and all those others. And we have this many on Mars. We need to treat it respectfully like that one and earn our way down there and realize it's probably going to take steps where you go to orbit first, then you're probably talking short stays, using the human beings to do what we have done an amazing job on ISS, which is using crews to hook stuff up and get the job done. Because trying to do it all robotically will take forever. I will talk. I love this picture right here because this is to scale what the Mars exploration program did, and this is over a 15-year period. So you got Sojourner in '97, right? It's tiny. When you actually see it there, it looks like something your kid drives around, and it was incredible when we did it, right? And then you got Curiosity, which is the size of an SUV, basically. You know, for human class landers, we're talking 20 metric tons, which is basically 20 SUVs, you know. So that's big. That's a big pain in the neck. And landing it is not going to work with our current technologies. We're not going to be able to use chutes. We already know that. We're using supersonic retropropulsion. So we got to step our way into that reality. And so that strongly suggests that the initial missions are probably orbital. You know, maybe you do a highly desirable in terms of a lander if you think it's ready and it checks out. Maybe you phase it in on a second or third mission. But just doing the whole round trip and understanding the logistics and how you do that and how you do spare parts and all that kind of stuff buys us so much knowledge that we're probably going to save someone's life. I love this one. We have been there before, and this is Antarctica, okay? And so this is Amundsen basically succeeded, and Scott failed, and they really were some fundamental differences in terms of how they approached. But one of my favorite ones, Amundsen and his teams actually went and lived with Arctic Inuit and the native Alaskans, and that's stepping, and they understood fundamental principles. So, for example, they understood you don't use stupid horses, because when a horse dies, the other horses can't eat it. You use dogs, and when the dog dies, the other dogs eat it. You know, so and that sounds dumb. And if you're a dog lover, that might sound horrible. But the point being is that they learned the lessons from others who had done it, and they stepped their way to it. They understood that logistics was make or break, that it would kill you if you didn't think it through, and they thought it through with all those lessons, and they pre-staged appropriately. And so that's something, those are, again, stepping it. And then on the Scott thing, you can see those are examples where they didn't do it right. In fact, a number of us actually wrote a little paper there, which is in a link there that was just released. But it's looking at both what was learned in Antarctica and what's been learned on ISS, and then try to guess maybe how it might apply to Martian logistics. But there's some really cool things that we all learned, even playing with those ideas. But there are the key points: stepping it, that small to big, earning your way up that mountain. ISS is amazing, and the 60,000 days, to be clear, is not ISS, although ISS is the big block of human days in space now. But it does include the Salyut, the Mir space station, and all those numbers. But humans know how to operate in space. You know, we know how to keep the body in pretty good shape. I mean, there is an eye issue that we're working through, but space is not the devil here. The devil to be overcome is the surface of Mars, and we have to be careful about how we step it. And I think I've covered most of this point, but it's really fascinating to look at how little time we have in terms of extended missions of people in there, and frankly, they're mostly Russians, which is and men, and you need. Yeah, they're working it. But the point being is that we really need a statistically meaningful set of data sets that show us that we either go asymptotic in terms of some of these degradations, or we don't, and then we know what we have to imagine. And then there's the whole return to a gravity environment that really strongly begs there. But ISS is an amazing platform for actually flushing a lot of that out. And that might be my last slide. Yeah, that's the slide. Anyway, we do have a distro if anyone would like to join our Twitter, but so that's our plug. Thank you.
Thanks, sir. So I'm going to give each of you a specific question, and then we'll open it up a little bit more. So Joe, when you talked about that design team and your focus, I think you said the word budget about 4 or 5 times, and I know that that's a really key driver in assembling these missions. But is it all about the budget, or is the technical and the schedule aspects and the technology roadmaps, does it all boil up to budget, or is it more complex than that?
Yeah. I think it's definitely interrelated, right? Because my example I used was for an orbital mission, you don't have to do the EDL problem, right? You could. I'm not suggesting, if anybody out there's from an EDL, technology team, I'm not suggesting that we just say, forget EDL, don't even worry about working on it right now. It's just that when we looked at it in the long poles, it was a 16 or so year problem, and I was on that team. I remember it really well. I don't know why they picked me to be on that team, but I had a bunch of Langley people with me and a couple of JPLers, all guys who knew, and gals who knew, that problem intimately. And I was the guy who kept saying, come on, if we had more money, couldn't we pull some of that up in parallel? And I know we're getting ready to do a high-end demo now and stuff like that. But when you start stacking it up and looking at all the things that have to be done to put 20 metric tons down, which is our minimum almost that we've got to do, it became a long pole. It really was a long pole. It was 16 years, and it was hard to squeeze it. So, and if you do squeeze it, pull stuff more up into parallel and do some of those tests or do them on a quicker cadence, that means more money. Just for that one. And then like Rick says, that one is only one of about 10 or 12 or 15 different things that you're trying to do to get ready. So if you can take one of those and pull it off the table or let it stretch out, that definitely keeps you back under that budget profile. So that's why an orbital mission, does relieve you a little bit on needing to have big increases in budget and still do the date, So my favorite thing, back in my system engineering background, is you've got cost, schedule, and technical, and usually you can get 2 out of 3, right? So it's that kind of thing. You're always giving somewhere.
Well, and if I might add, so I totally agree with what Joe said, and I think it's the risk too, right? Can you get going on something sooner than later so you inform your entire risk profiles that you're dealing with? Right now, we don't really know about it because we never get going. And I know there's a tendency to want to say, and I personally worked console when we put a urine processing assembly on board ISS, and a miserable experience. But I will tell you that we made it work, right? But the key part is we have to understand what the failure modes are. You need just run time to understand your mean time between failures on those things. And you're not talking major upgrades on these things. So the orbital piece, actually, thanks to a lot of the work on ISS, is largely known, I would assert. There are strategic things you want to do, and there many of those things are being worked on right now. But you're not going to see, if you're going in the 30s, probably you're not seeing major changes in some of these technologies, I believe.
All right, thanks. So Jen, you presented, I would say, kind of a very diverse set of science that can be done in orbit. And I think one of the things that comes up in the comparison, though, is that diverse set of very valuable science, how does that compare in significance to actually, the end goal of boots on the ground?
I think it's just as valuable, but to the point of what we've been talking about here, if you land on the ground, you might not do any science because you're worried about staying alive. So, you don't have the time that's required to, I mean, you may have lofty ideas and goals, but in reality, it's probably going to be much harder than we think it is. And so science is going to be, put as a lower priority than staying alive. Also, if we send send something boots on the ground, we're likely going to be more concerned about mass for EDL reasons. We won't have the kind of lab that you would require to do not only the surface science, but some of the back and forth science, some of the really cool stuff that you can do to understand, to take advantage of this unique environment in terms of radiation and microgravity. So it's interesting because I really change my mind on this the more that I think about it and the more that I learn. And I think that you're going to get more science actually out of an orbital mission than you would out of boots on the ground at this point.
Especially for that first boots on the ground.
Yes, especially for the very, very first one.
Interesting. So Rick, you talked a lot about how it's safer in orbit, as well as your concern over the unknown risks. And I think that in orbit today, I think we still need to learn a lot more about that length of time in zero gravity, the radiation environment, and so on and so forth. And I think that there's unknown risks there. And ISS is a good analog, and I think Gateway will be helpful as well. But can you talk about the unknown risks that we can imagine that face us in orbit compared to the unknown risks that face us on the surface?
So I would just go back to the point. I don't think you have a choice. And let me explain that. You have to be able to handle the contingency of not being able to land. By definition, and you have to be able to handle keeping a crew busy on the outbound and inbound legs. Otherwise, they're either going to shoot each other, kill each other, or you're going to shut off the comm to the ground because they're going to be so ticked off. We have to learn to come up with a science strategy and plan that actually really utilizes them as the creative human beings that they are. So it's not a question, and we're going to have a contingency that actually handles the radiation exposures there. And most of the HR human research guys I know they're not so much worried about the in-space piece, although I'm not totally convinced they've thought through the whole 1,100 days with a contingency. But they're more worried about cancer mitigations once they come home. And whether or not there's creative strategies that can be done to mitigate that. But the point I think is that it's not an option. You have to basically plan for the full 1,100 days in space, and we have to understand how to manage that. So that's my belief.
What about the surface risks?
Well, I mean, the general assessment is that the surface radiation, because you got the planet blocking the sun, right? You've got something of an atmosphere, is that it's like being on ISS, essentially, in terms of dose. You've probably got a galactic cosmic radiation that's there that you don't necessarily have on ISS, but the dosage rates are very similar. And there are ways to mitigate it once we got enough infrastructure. You can put regolith on top, you can put water on top, you can actually have the crew sleep underground. So that the aggregate dosage rate is actually manageable. There are a lot of things we can do, but that requires a kind of activation and checkouts that we did on ISS, frankly, that, in the initial days, and Jen's dead right, in the initial days of ISS, we did squat on science. And in fact, Huntsville, which manages the science program, was always, second-rate fiddler. And in fact, we had to kind of go through a whole lot of discussion once we finally got everything up and running, because that is the priority now, and so I think you'll see a similar transition as we learn to set up all the infrastructure that's going to be needed to sustain human beings on the surface of Mars. And we'll see it on the moon too. I mean, the same process will occur.
So one thing that's come up when we talk about the different risk profiles of the different types of missions and what we ask the crew to do and what we ask the types of risks for them to take is why take the risk of going to Mars if you're not going to be going to the surface? Is that something that's unfair to ask the crew to do? So, thoughts?
That's a really good one. I can remember it was another one of the AMs. I can't remember if it was 3 that we talked about that. And we had a couple of astronauts in our group. And I know, there's the aspect of you're going all that way. You have, all that expense invested in this and your personal risk that you're taking. And yet you're not going to be able to say you stepped on the surface. And we talked a lot about that with them, to be the first person on Mars. You're one of the first few that are in orbit around Mars. You get to look out the window and see it, like Rick's great picture he had up there. But there was a lot of debate about that, I can remember, and I think there is that aspect of it psychologically maybe that, we all have this thing of, if we're going all the way out there, we want to put our boot on that thing and get down to the surface and actually see it. But from a really practical standpoint, a lot of these arguments, I'm sort of like Jen, I'm sort of swayed by some of the practical arguments to say, maybe we ought to think of it more like ISS, where the first few missions are really there to set up that eventual step on the surface. Do some of the site preparation like Rick was saying. I was thinking the other day about this too. It's a little bit contrary to what I said earlier about being able to defer all the EDL stuff, but let's say you had a crew in orbit around the surface and you wanted to try this first 20 metric ton drop to the surface. You've got them right there, so you can better monitor what happens. The whole thing of what's going on during EDL, we're always waiting, what was it on Insight, at least 8 minutes before we knew,
Minutes of terror.
Yeah, exactly, but it's all happened already, right? So I was when Insight was landing, I was up on the hill over here talking to one of the staffers, and he said, so, when did it actually land? And I said, well, it's already either crashed or or it's all good.
And the bandwidth for telemetry is like that.
Yeah, exactly. Right. So there is, that aspect of it. And then, the other thing is, if we're going to make propellant on the surface and we got crew out there, and let's say something goes wrong in the ISRU process while you're filling tanks, if you're right there, somebody can say, ooh, that pressure's getting too high. Shut that thing down. Let's wait and see, we can reset and try it again. If we're doing it all remotely from Earth, we might blow a tank up, and we will find out about it too late to do anything about it. So there's a lot of aspects as you start to think through this that it is a little bit like Rick was saying, and maybe then we start doing these short sorties down from orbit to say, okay, now we got to hook these two lines up between these two pieces that we drop down, and those folks go down and do that and then go back up, and we're setting it up for being able to put crews down and stay for the full 400 days or whatever. So it's a different way of thinking. I mean, that wasn't the way I started out either, but it might make sense to do that.
If I might add too, I totally agree with everything Joe said. I think if it's Apollo 8 did this, right?
Right.
So it's not like we haven't done this before.
Right.
And so I think it's a difference between an individual mission versus a campaign of missions where people understand they're part of a larger whole.
And actually today I just saw something in the news. One of our friends at Aerojet Rocketdyne is Tom Stafford, and they were talking about going down to 47,000 feet above the moon and not landing. And he in turn had to do that, and just say, oh, okay, we're that close, but we're not going to be the first one.
Yeah, and I would add one other thing. Mars is. I actually always say that Mars is a belief issue. It is not a technology issue. It is a belief that is so hard that it is impossible. And the first crew that goes out there will forever crush that belief, because human beings will have gone the 175, 200 million miles or whatever it is, all the way out there. And human beings, when a little kid is in school, will say, human, that's part of our sphere.
Right.
And going to the surface is a done deal at that point, because human beings just accept that as part of what they can do. And when people accept that they're capable of something that incredible, they do it. So,
I mean, imagine how devastating a failure would be on the very first mission if we sort of overshoot. If we are confident that we can orbit, then I mean that's just building the excitement and we're definitely going to go back and boots on the ground. And the other thing I really liked, sort of the mountain analogy. I mean, you don't climb Mount Everest before you climb a ton of other mountains. You don't just go.
Okay. Yeah. And so one question for you, Jen, as far as the transit vehicle having a lab and the crew being able to work in that lab, are you going to let them touch the samples from the surface?
I mean, that's a good point. I think that there are some things that they may be able to do without physically touching them. There's a lot of spectroscopy. There's a lot of non-destructive and even sort of non-fiddly things that you can do. And I think that, if you're going to send a lab, you should send some scientists as well. I mean, I think you've got to send some astronauts who are serious scientists. So.
Could you have a glove box? I mean, could you have something?
Yeah, there are things you can do, but yeah, I mean, that is a good point. These samples will be absolutely precious, and there probably will be scientists that are really pissed that they will be touched by others. But I think there's a lot you can do without it, and still have samples to bring back.
And just to build on Jen's point, it doesn't mean that you just have the limited samples that we're targeting for MSR, which is the first round trip demonstration. It might be that you actually do multiple launches and the crew picks them up. And maybe there's a subset of the samples that you're willing to put at risk.
Or don't fit.
And then the other piece you need to realize is there's no guarantee the crew's going to make it back successfully. We assume that, and we work very hard to do that. But if we can get incredible science done in situ sooner than later, it means that if you run into that risk, you've actually already got the science done.
So my next question is a little bit more of an architecture question. When we look at the constrained budgets and we look at all the different systems that are required to keep crew alive in space, it raises the question of why separate your transit vehicle from your lander? Why separate that functionality? Why not have, maybe not a single vehicle that does everything, but combining functions into things, which would kind of mean then, therefore, that your lander is your part of your transit system, and you might as well go land on the first mission. So, thoughts on that part of it?
Go for one. Somebody has a concept like that it's all in one vehicle. I think I saw something like that this morning. I just have a fundamental objection to that. And again, it goes back to my system engineering background. If you look at how we architected Apollo, how we were going to architect Constellation, there's a reason that those vehicles are separated out because they're specialized. And even down to the propulsion, you need different kinds of propulsion for different phases of the mission and things like that. And if we don't have to have the same heat shield work to come into Earth's atmosphere as the one that goes into Mars' atmosphere, it allows you to optimize the vehicle for that thing that it's supposed to do. And to me, that's always seemed like that's the more, elegant solution. And at the same time, I don't think it's really the more unaffordable solution because, a lot of that stuff translates into mass. And if you're not resetting the rocket equation, if for some reason you can't do that, which I'm not convinced you can for those kinds of quantities of fuel and things like that, that's a little bit of a step jump for me. Then you are constrained to what you can launch and package together, and that's where we come up with things like a 20 metric ton block that has to be put down on the surface. So I would say that, the lessons of Apollo and the lessons of other programs that we've done since then sort of have taught us that that's the way to go when we're trying to do this kind of a complex mission where we have multiple, phases of a mission where I don't want to make one type of thing fit all those phases and therefore be non-optimal for all of them.
And I think I would maybe add to what Joe's saying too. I think so. I'm an aerospace engineer. I like airplanes. I fly them. I would say I think we have been very dominated by airplane thinking. And rocketry, right?
Space ain't airplane.
Yeah, and space is not airplane. It's more like a submarine.
Yeah.
And and I would assert that if you had a more balanced view of it, and also remember, I was making an assertion that we treat the in-space piece as like, oh my God, it's really hard. But I think we've actually learned enough to know that SpaceX is doing an amazing job, and some of these other companies are, in terms of reusability for the ascent entry piece. We already have reusability for in-space pieces. It's called ISS,
Right.
And it's been remarkably robust. We haven't used a fraction of the EVAs we thought we needed to do things, and so I think it's a different type of reusability, and we're kidding ourselves if we think we can just lump everything into one thing. I think you're missing an opportunity. And the other thing I would say is cubic meters per crew member matter. And so when we jump from shuttle and Soyuz to the space stations, people are in space for 6 months. They just need more cubic meters. I am not convinced we have a clue as the cubic meters that are needed when the Earth is a tiny blue dot way off the thing, and Mars is a tiny red dot, and you're in the vast sea of blackness of space. And I don't think we totally understand how much a human being needs in terms of cubic meters, because that number's been changing as we do different types of missions. And so the beauty of treating a in-space component is different, is that you can aggregate additional pieces and get that space you need as you learn that you need it. And you've got really cool things like what Bigelow's doing with inflatables. The Indians are doing similar types of things where you can actually grow your in-space cubic meters per crew member. And I think we need to have the humility to realize we may not be able to come up with the one-size-fits-all answer, and use these environments for as they really are, not as we would want them to be.
But is a multi-module system perhaps contributed from different companies and countries add too much complexity?
So I cannot tell you how many times on Mir and ISS that dissimilar systems and modularity kept people alive.
I will even go further. I would say, that's what saved the astronauts on Apollo 13.
Yeah.
Dissimilar
That's
redundancy.
Right.
It came up in our panel earlier today too, and I'm a huge believer in that.
Yeah.
Yeah, I think I got one more question, and then let's open it up for the room.
Not so fast.
We've got till 5:30. Yeah. How does politics affect this choice, both from a needing to have a political win perspective, but also from a policy perspective?
You're saying the choice between orbital versus boots on the
Yep.
first flight. Okay.
So I'll take a stab. I think you have to earn your way. And by executing achievable missions that are delivered on cost, on time, systematically, is the way you do that. And so part of that is the stepping, and understand how you step this. And we have to prove that we can execute these never attempted before missions in a way that is believable. And I think if you do that, the American public and its politicians will say, wow, that's pretty amazing. If we consistently keep coming in over budget, behind time, because we grabbed for too much, in other words, we went straight to the end state, nothing will ever happen. And we'll be here 20 years from now, I'll probably be dead, right? Where we are basically wondering why Mars hasn't happened yet. It's a temporal organizing that is critical, I believe, not only for the reasons we talk about, but for building support and believability. That's
Yeah, I would say too, I think if you set up the right milestones and You know, it's a little bit of expectation management.
Yeah.
But you could definitely make that a win, especially now, you know, when we have high def cameras and things like that. I mean, I'm just picturing I love that picture you had there. But, you know, just imagine, here's our crew, here's Mars, you know, in the background. We've got a big picture window and everybody's in front of the picture window looking, you know, with Mars right there. And we're doing great science. You know, we could claim, you know, this is the first time we've ever been able to do this. We brought those samples up and we're actually looking at them in the lab. There's a lot of things you could, you know, as a politician, you could say, I was the guy who got that done, or lady that got that done. And I think that, you know, maybe we've matured a little bit from we've got to actually be physically on the thing that we're going to. And certainly I think we've gotten past the idea that we're going to just go out there and run around and stick a flag out. I mean, that's what I hear more and more these days is we don't want to do flags and footprints. You know, people repeatedly say that. So if everyone understood that it was part of this campaign of missions, like Rick said earlier, and that, you know, we are going to actually accomplish a lot of really cool things. We're burning down risk. This is getting us ready. I think you could, you know, potentially make the argument that you could keep that sold. And, you know, I think that's been our challenge on all the AM workshops that we've been doing is everything we've done, we've tried to keep the sustainability aspect in mind, that we're doing something that sets us up for the next thing, and that it's just going to keep on going. And that you know, we don't do something that somebody at one of the workshops made that point. They said as soon as you achieve the goal, then you are on the chopping block. And so what we try to do is keep moving the goal.
Or set a campaign.
Yes, exactly. Right.
Something interesting from a scientific perspective to think about is what kind of discovery could impact, you know, political will or desire to go. And yeah, exactly. And so imagine if we did find life with some sort of robotic asset. So it's, you know, that has all sorts of other ramifications for science and exploration, but it definitely makes it more appealing in some ways to politicians. I think it may. So that's just an interesting sort of thought experiment.
Mm-hmm. All right. Well, why don't we go ahead and open it up to the audience? And we're recording this, so microphone's coming up.
Okay.
Wait for the mic, though.
1968, I was 20 years old. It was one of the worst years in U.S. history. I won't repeat that. All of a sudden, on Christmas Day, Apollo 8 went around the moon. The whole country the morale shot up. Everybody, all of a sudden, we believed in ourselves again. We forgot about all these bad times. We were positive and optimistic again. I'm making a point, building some foundation. Be patient with me. 50 years later, I read the definitive book on that mission, and nobody at NASA believed it would work because that Saturn V, you had 5,600,000 parts and components that all had to work right and together. The three astronauts, Borman, Lovell, and Anders, told their wives, get ready to be a widow because we're probably not coming back. James Webb took it all the way up to LBJ. I'm getting ready to make a good point, all right? And LBJ said, this is a big, crazy risk, but let's do it. Because he sensed one thing, that if it worked, it would be a tremendous shot in the arm for the American people. Now, let's go ahead. Some years ago, Dennis Bigelow put together a nice concept that was going to be privately financed to send two people in orbit around Mars. Basically, I think you know what I'm talking about, the capsule,
Tito.
then the Bigelow,
Yeah.
Okay.
Yep.
Instead of, when Christopher Columbus went out to explore the New World, he didn't tell the boatyards, build me a new super ship for this strange world. They just took what they had and they went for it. All right, no, that doesn't mean being wild and irresponsible and foolhardy. It means work on what we have now, get an orbital mission together, and make it where it most likely will work. And then all of a sudden, it's just a tremendous shot in the arm. All of a sudden, Congress is appropriating money, private investors are, everybody's pocketbook opens, and that's the suggestion is and I see all these beautiful modules and systems, and they have a lot of merit, but do we really need to get that complex? Can we do something simpler to begin with, just to get the show off the ground? That's my question. Okay.
Yeah. Thanks, Jack. That was kind of what El Cheapo was all about. So.
Well, and to build on that, I mean, it's not only the shot in the arm. It actually, you're learning. I mean, and you're buying down those risks, and that's really massive. So, and I love that example in terms of the shot in the arm, because that's really cool.
Go ahead.
I have a question. I would agree with Jen, to start with, that when you do land on Mars, the last thing you want to do is a lot of science that doesn't have anything to do with survival. The only science you want to do is the science of survival, right? And that's true for the orbital mission too. That anytime you're going on any kind of space mission, the object is survival to start with. That's our mission here, right on Earth, is survival. I'd like to survive to get home tonight for dinner. Anyway, other than that, I would contest everything you guys said, everything. And that is, if you want to design an argument for not landing at all on Mars, then you've got it right there. You don't have to do anything else. You've won. And so I'm saying that, you can take baby steps and work on it every synodic period, and maybe by 2099 you might try a landing mission, but I don't know. And so I'm saying that baby steps are okay to a certain point, but I would contest all the arguments you guys have made about not doing a landing mission to start with. And nobody has mentioned the moon. And if you do the moon right, which means using the moon like a small Mars, and you go to the moon with all your landing infrastructure and all the procedures, hardware, software, and everything you're going to use on Mars for a landing, and use it for the moon, and then you make changes to make it improved and correct critical problems, and then you do it 3 or 4 more times, and you establish bases all over the moon as if it were Mars. Then doing Mars is just like adding another base to the moon. You just do it to the moon. You do it to Mars as you did it to the moon for 3 or 4 times. The only difference is you have a longer trip time, and Mars is a little more gravity. You can adjust for that.
And an atmosphere.
And an atmosphere.
And
So that EDL problem's still there.
A very thin atmosphere.
But it's a big problem, and we really are talking a different class of lander with a different landing technology, and we got to grow to it. And I'm not advocating waiting till 2099. I'm saying you put landers on as soon as you're ready, and you've jumped up that 16-year curve, and you get it on there as soon as you can. But you don't make it a mandatory objective for the first missions there, because you're setting ourselves up for failure. And I think it's a difference between mandatory objectives and highly desirable objectives. And in the shuttle world and in the station world, we are very crisp on those objectives and understanding which is in which bucket. And so I just would try to encourage you to realize that we're not saying delay landing, but there is a belief issue in terms of the obtainability of Mars, and the orbital missions completely unright. If you're that first crew, they will be so proud that they served in that capacity in terms of overcoming that belief issue. It will be incredible, I believe.
Yeah, Mike, I'd also point out we did have in El Cheapo, 33 was the orbital mission, 37 was the first boots on the ground. So we did skip a couple of opportunities, but we also weren't suggesting that we'd wait forever. Like I say, I wasn't a big fan of it either at first, but as I am learning a little bit more and talking with folks who really understand the problems and things, it's kind of won me over a little bit.
Okay. Well, I would accept that argument. That I would still contend with, if you did the moon right, then you could consider a landing mission on Mars for the first one, and you can go there with your lander and all that tested out, with precursor missions already landed on Mars with a complete spacecraft to go back up to orbit in case your your landing spacecraft to do that doesn't work. And if you can check it out, you can do a lot of science for 2 or 3 weeks or a month. When you first orbit Mars, satisfy yourself that you have a lot of good science on, well, you wouldn't do the science on the landing site, because the landing site already has your precursor mission already there with infrastructure landed and maybe a lot of supplies that you would use for the first several months. So you know your landing site. You don't have to decide which landing site, but you can do a lot of studies, and then you can check out a lot of systems. And yes, if your lander in orbit around Mars for that first time showing problems, and you decide it's a high risk to use that lander, then you can abort the landing part of that game and come on back. You can always do that, as has always been planned for all the missions. But my contention is if you do the moon right, you can do a Mars landing the first time. But,
Sorry, I just have to go after this issue. Moon feeds forward in areas like rovers, suit designs, HAB labs, and a number of those areas. The lack of an atmosphere is a big issue. And I do not agree with you that you can buy down. You can get the Ascent vehicle piece maybe, but you cannot get the lander piece. So, and frankly, I love some of the guys that do the EDL at Mars. I love one of them. Basically said every time we land, he gets post-traumatic stress syndrome because it is hard, and we have never put the 20 metric ton landers down ever before. Nothing even in that class. There is a massive learning curve, which is driving that number that Joe is talking about. I just think it's a little more challenging than maybe the way you're characterizing it.
I think if you do it right, you can reduce that challenge to a low.
Maybe.
To be acceptable.
And one thing that you made me think about is that if we see all the benefits of an orbit-only mission, and we plan that first mission to be a landing mission, but for whatever reason, whether the lander's not ready and it's there, and we decide to do an uncrewed landing, or it doesn't show up because of schedule delays, maybe that is a different way to plan it, right? Plan to land, but accept a higher probability of not being able to land.
Right.
Yeah.
There's a lot of psychological issues with that, though. I think.
Yeah, that is true.
Managing it.
Well, you're going to have to check it out when it's ready. I mean, it may be that your core mission is you do the orbital. If you have a commercial partner or an international partner who takes on the task of a lander and you get warm and fuzzy that it's really ready, does all the checkouts, then you go execute your highly desirable. It's a question of, do you hold up the first mission to Mars and all the learning that comes with it, waiting for the technology development to be done? I would assert we are actually getting ahead in achieving what you're after by going sooner than later.
What do you mean by doing an orbital mission sooner?
Sooner.
Rather than wait.
Yeah, rather than wait till you get all the tech development done on the EDL systems.
Which was what Apollo 8 did,
Yeah, that's right.
The lander wasn't ready, so.
Yeah.
Well, Apollo 8 was different because the moon is only a couple days away.
Right, but I'm
Mars
just
is
saying.
more than a couple of months away.
Wasn't the original plan, though.
Yeah. If you
It
take
got
that
pulled out of
argument and
sequence.
extend it, sometimes you can see a little bit better if you take an argument and extend it to maybe an unjustifiable point, but to an extreme point. If we decided to go to Alpha Centauri because there's a planet around there that we want to explore, would we go there to orbit first and then come back and then decide we're going to overland? And it takes about 40 years to get there.
Right. If we decide to go there and we want to get there in like a human lifetime, our biggest problem is going to be stopping.
So the first mission to a star would be a flyby, right?
Right.
Fly by and not come back.
And not come back.
One more question, and that is,
Sure.
do you know with SpaceX, do they plan to have an orbital mission to start with, or are they planning to have a direct landing mission?
No, I can tell you because we work pretty close. They do not plan on an orbital mission at present. They have one system does everything,
Right.
And their intention is to try to land. I personally don't agree with them on that. I think that they're going to find out it's more complicated as they get into the details of the architectural planning. But if they can do it, more power to them.
I actually don't think they have enough delta V to go into orbit. They have to land.
That's
They have to
Yeah.
airborne.
Yeah.
So it's like, if they can't land, they can't also not orbit. They
Right.
are screwed.
and they have to have enough ISRU production to fill that tank back up to get back off the surface. So
that's a no return either too. Okay, great.
Well, and they're planning on using water, and the water has to come out from someplace, and they're planning on using subsurface ice, and we haven't characterized. And there's just a whole. But you know what? They'll figure that stuff out.
right.
Yeah.
Okay, thank you.
Thanks, Mike.
Okay, Rick, I've been corrected by the ISS program. We're up to 65 hours of utilization time per week. So I have to get that on the recording so I don't get in trouble.
But is that with 4 or with?
It's with the 4, so it's
Okay,
not our
cool.
baseline, which is 3. So
Okay.
3 USOS crew.
But we fight for it.
So we fight for it. And when we had the mishap, I had to go just to 3 crew earlier this year. That was, of course, not 65 hours.
Yeah. That's fantastic. But we, in the original days, fought really hard to even get up in the 30s. It was hard.
Yeah.
I have a question. All right. So if we decide we were going to do this orbital mission in 2033, we could do the El Cheapo that Joe outlined, and it's a 950-day mission. They're going to be a long time at Mars. If you wanted to be more complex, you could send up a second return stage for more Delta V. You could have a deployable sunshade on the transit hab.
Come inside.
And so
Yeah.
it's possible in 2033 to do a 570-day mission.
Yeah,
It's
that's
more
what you
complex,
should. Yeah.
but the crew would get to go to Mars and they would get to go to Venus. What do you see as the trade-offs of that? Do you think it's more preferable to do the more complex 570-day mission, which is shorter, or to do the simpler, longer stay mission?
Wow. I like your idea. It's cooler, and so pros and cons. Shorter for the crew, right? So it's more in line with our experience in terms of human health. Although, as you pointed out this morning, we are sending them in closer, so they are going to be in a region that we haven't had people before. In terms of if there's a bad solar flare or something like that, and
have a shelter.
yeah, and it'd have to be a stronger shelter for that, and we've got to have that additional stage sent out. So we're adding some budget for that. So again, I always come back to cost, schedule, and technical, and there's sort of. I think we're gonna break out somewhere there. So if we were really trying to just say, let's go and do all the things that Rick wants to do some of what Jen wants to do, probably I'd stick with El Cheapo, and we get more time on the target by doing it that way too.
So, and Javier, that's a cool question. I mean, obviously going to Venus would be great. But I think there is a value in repeated operations, and I think on those windows, it's tied to Windows when you really get those opportunities, as I recall, right?
It's like every 11 years.
Right. Yeah. So, I mean, you're taking not a one-off, but a 1 every 11 year off, right, to do it, whereas really we're talking going every synodic period largely. And if you're doing that, you really want to understand the ops and the cadence that we want to have there. And that's actually the learning of that first mission, right? You get the whole rhythm down, you get the logistics down, you get the sparing down, and all that kind of stuff. And in my mind, there is a beauty there because you get the lower mission time, right? But you're not really getting into the cadence of what your long-term sustained approach is.
I'm listening, and of course I want those boots on the ground, but I'm not stupid. I mean, I do realize that with the fickleness of political leadership, a major accident, because we were overreaching, is probably a really bad idea. That said, if I listen to us all and knowing the workshops we do and the reports we write, I do believe we really need to get a workshop going with the PR people to make a PR plan on how to sell this to the public over the next 14 years, 16 years, 18 years, so that the public knows that this is the cadence and that's why it is. Because the thing is, if we in-house decide that this is safer and we need to do an orbital, and we have all this hype, which ExploreMars is part of, about boots on the ground, and we don't prepare that really well PR-wise, that's going to cost us, and it might cost us everything.
Well, Artemis, I would push back on that a little bit. I mean, the idea of a crew that's actually the drama, the story of going out for 3 years. I mean, that's a Lewis and Clark expedition, except we're bringing the public along. I mean, and if it's part of a campaign, a clear campaign, and if it's multinational, right? It's like ISS. You're not going to cut it off. It's impossible it becomes essentially a self-sustaining thing in and of itself. You know, the trick is you got to get going. As long as it's on drafts, boards, that's easy to cut it. But once you actually have a real hardware in place and you got people training and you're doing it and it's multinational, that thing is just going to go. And when you're in the Martian system, and when we are in the Martian system, we're going down to the surface. It's not a question of time. I personally view it this way. If all of us together could make this happen and we all went off the bus, off the edge of the cliff tomorrow, we would be going to the surface and we would have made a massive contribution. It's that simple. And otherwise, it's going to be drafting projects until then. Sooner is better than later if we can actually execute this, because it's a belief issue. I fundamentally feel that it's impossible. And when you send people that far and you learn how to do all those things and get the cadence that we just talked about, you know what? People realize this is not that hard. We're up to it. I would actually turn it on its head. If you don't do this, it may never occur.
But the overall point of dispelling rumors, it's going to cost $1 trillion to go to Mars, and dispelling rumors about the radiation's going to kill you during the trip.
First 5 days, right?
Right. And laying out the campaign, laying out the risks, laying it out for the public in a way that's
that's fair. Yeah,
understandable. I think that's helpful. And then it's also helpful to have some advocates like Representative Perlmutter on the political side, who's just all in.
And you speak to your point. If you're ready to do the landing, and you make it clear that that's something. If we think we're ready, we'll go attempt to do it. Yeah. That just adds to the drama of the whole thing. I mean, and really in the total return on investment.
Yeah. Yeah, that's what I was saying earlier. I wouldn't say we slow down on any of the EDL work. We keep it going, but then, we're not forcing it to fit into that 2033 opportunity. We're saying it's well along, we're almost there, and we got one more test we really need to run. So we're going to go ahead and do the orbital mission. And I think, I don't know what the percentages are, but I bet you it's way up above 80% of all the other stuff that we need to burn risk down on, that we're getting done with that orbital mission. And the science part, I mean, that's the other thing I'm really swayed by is, both from your saying, Rick, that the crew needs to be busy, and Jen saying there's a whole lot of cool stuff we could do both on the way out and on the way back. That I think in itself is a great reason to do this mission, because we've got humans out in deep space doing science, and we're learning about the physiology of the humans out there. We're doing science that we can't do anyplace else. It's all good, and we're getting our mission ops down, right?
Go ahead, pass back the mic.
Whoops.
I was talking.
Like the mic.
Thanks. I worked for our North American Aviation in the 60s and on the Apollo program. And this gentleman here is very correct. When we did the orbit up Apollo 8 around the moon, the view of the country on space skyrocketed. Yeah. And we didn't have to land at that time. Right. And so it was a great thing. Well, I was working at North American when they had Apollo 1 fire. Yeah. And when the news came out that we burned astronauts on the pad, didn't have any liftoff, there was 24 hours of deep depression at North American Aviation. A lot of us thought, that's the end of the space program, we'll salute to the Russians and say good luck, and because we failed. Yeah. But then very quickly it came back, and I didn't have a good thumb on the society's view on space at that time because I was too busy working. But at the company at North American Aviation, people buckled down, and they said, "We're going to fix this thing." And so I think the idea of a failure is that it supports your determination to attain that goal. And that the society would drive even harder if we went to Mars and we had a lander mission, whether it was the first one or not, and it failed. I think the American society would say, we've got to make that successful. And so they would increase the budget and drive for a more secure mission. So I think that's what's going to happen. And I think that in answer to another question about the political aspect, I think if you go to the politicians and say, gee, we're not quite ready to land yet. We got to do another orbital mission around Mars, and we'll land in 2044. But we got to secure this hardware and software and all our procedures, and we can do it better to orbit Mars first. I think they would accept that. They have always accepted engineering and science rationale more than their political whims in the past. Might change in the future, but I think they would accept NASA's viewpoint. NASA has a good reputation, and they would accept NASA's judgment. So I don't think that's a problem, but that remains to be seen, of course, at that time.
Thanks.
Other questions? All right. Well, thank you for interacting with us. Thank you very much for the panelists. I think we had a very good discussion, and I hope everybody's going away with some things to think about. So, thank you.